Today we are solving LeetCode 54201 matrix. This is a medium level problem, but it teaches some very important DSA concepts. In this problem, we will learn 5 key ideas. First, how to treat a matrix like a graph. Second, how to move in 4 directions inside a grid. Third, why BFS is useful when we need shortest distance. Fourth, what multi-source BFS means. And fifth, how to carefully handle rigid cells, distances, and matrix boundaries. This problem looks like a matrix problem, but the real concept behind it is graph BFS. BFS means breadth first search. Let us understand the problem statement first. We are given an m cross n binary matrix called mat. Every cell contains either 0 or 1. For every cell, we have to return the distance of the nearest 0. The distance between two cells sharing a common edge is 1. That means we can move up, down, left, and right. We cannot move diagonally. For example, if the matrix is this, the only one is at index row 1, column 1. Its nearest 0 is just one step away. So the output will be this. Now let us take the second example. This is our second matrix. For the last row, select row 2, column 0 is one step away from the 0 above it. Select row 2, column 1 is 2 steps away, is again, yes, it is 2 steps away from nearest 0. And select row 2, column 2 is one step away from the 0 above it. So the output becomes this. As you can see, it is just one step away from its nearest 0. So it is 1. The same applies for these two also. But for this, it is 2 steps away from the nearest 0. Either we go this way, or this way, or this way, or this way. Like go up and right, go up and left, go right and up, or go left and up. It will take 2 steps to reach. So now let us think about the brute force method. For every cell that contains 1, we can search for the nearest 0. One way is to start a BFS from everyone. So start BFS at everyone. For every cell that contains 1, we can search for the nearest 0. Whenever we find a 0, we store that distance. This will work, but there is a problem. Suppose the matrix has many ones. Then we will start BFS again and again from each one. If there are m into n cells, then the worst case, one BFS can take m into n order time. And if we do this for many cells, the total time can become it will be m into n square. That is too much. So we need to optimize. Now let us think differently. Instead of asking for everyone where is the nearest 0, so instead of asking this, we can ask if all zeros start spreading together, when will they reach each one? So we need to ask this. If all zeros start spreading together, when will they reach each one? That is a key idea. All zeros already have distance 0. Their immediate neighboring ones will have distance 1. Then the next layer will have distance 2. Then the next layer will have distance 3. This is exactly what BFS does. BFS explores level by level. So if we start BFS from all zeros at the same time, then the first time we reach any cell, that will be shortest distance from the nearest zero. This is called multi-source BFS. So we are not starting from one element, but from multiple elements. We start from multiple sources. Here, all zero cells are our sources. Now let us define the algorithm. First, find the number of rows and columns. So our algorithm will look like this. So first we find the number of rows and columns. Then create a distance matrix of the same size. Initially put -1 in every cell. Why -1? Because -1 means this cell has not been visited yet. Now create a queue. Go through every cell of the matrix. If mat row call is 0, then distance row call is equal to 0. So initially put now create a queue. Then go through every cell of the matrix. If mat row call is 0, go through every cell of the matrix. And if it is 0, then set distance row call equal to 0. And push this cell into the queue. So why are you pushing all 0 cells? Because BFS has to start from all 0 cells together. Now we start BFS. While the queue is not empty, take out the front cell, let it be row, comma call. Now check its 4 neighbors, row -1 call, row +1 comma call, row comma call -1, row comma call +1. For every neighbor, we must check two things carefully. First, the neighbor must be inside the matrix. That means the new row should be between rows and 0 and new call should be between calls and 0. Second, the neighbor should not be visited already. That means distance, new row and new call should be -1. If both the conditions are true, then we update distance, new row, new call by distance row call +1 and then push this neighbor into the queue. At the end, distance will contain the answer. Let us write the pseudocode. So first we initialize rows and calls. Then we create a dist matrix. Then we create an empty queue. Now we run from rows from 0 to rows -1. We create a loop and we run from calls from 0 to calls -1. Now if the value of mat row comma call is 0. Then distance row call equal to 0, and we push this into the queue. Now we define, this loop will continue. Once the loop ends, we define directions equal to up, down, right, left and right. While queue is not empty, now we start a loop on the queue to do sourced BFS, multi-source BFS. While queue is not empty, row comma call equals pop from queue. We take the last element of the queue one by one, and for each direction, we compute the new row and new column. Then we check the new row and new column inside matrix. If they are inside the matrix, then we proceed and check the second condition, that is the distance should be double equal to the distance matrix at the new row and new call should be equal to -1. And if it is the case, then we update the distance matrix by distance row call +1. Then we push the new row and new call into queue. And finally we return list. Okay, so that is the pseudo code. Now let us write the Python code. So let's comment everything else out. Rows equal to length of matrix, and calls equal to length mat 0. And we initialize dist of the same size with all values equal to -1. Then we initialize the queue. Now we add all 0 cells as starting points by running this loop. We traverse across all the rows, then we traverse across all the columns. Then we check the condition. If mat r comma c is equal to 0, we set the dist equal to 0, and we append that in the queue. Once the loop ends, we now set the directions. The 4 directions are up, down, left, right. Now we loop through the queue. So we write while queue is there. We get r comma c by q dot pop left. So in the queue we store each element refers to the row comma column. Now for the different directions. So every direction is a row vector and column vector. So dr comma dc, direction row, direction column. In directions we update the new row and new column by doing this. Now we check if the new row and new columns are within the range. And the dist matrix value of dist at that new row and new column is double equal to -1. Then we update the value of new row, new column, dist matrix. And finally we append the new row, new column into the array. Now Once the loop ends, we return the dist. So that's it. Let us dry run the second example. So this is our mat. Initially, the distance matrix is like this. Now we scan the matrix. Wherever we see 0, we put distance 0 and add that cell to the queue. So after scanning, dist becomes this. All 0 cells are now inside the queue. Now BFS starts. The 0 cells will try to visit their neighbors. Cell row 1 column 1 is connected to 0 cells around it. So it gets distance 1. Now distance becomes this. This is the new dist after it has after visiting after BFS starts and it visit this row 1 column 1, row 2 column 2. Or because we are using this zero base indexing, so row 1 column 1. Now cell row 2 column 0 is neighbor of row 1 column 0, so it gets distance 1. Cell row 2 column 2 is neighbor of row 1 column 2, so it gets distance 1. Now distance becomes this. After second layer BFS, not second but first. Now cell row 2 column 1 can be reached from row 1 column 1 or from row 2 column 0 or row 2 column 2. The shortest distance is 2. So in layer 3 it becomes finally all the elements are now non-negative. So it ends here. What we are doing is a very simple thing. We are just first we had added all the zeros into the queue. So let's track our queue here. Queue contains 0, 0, 0, 1, 0, 2, 0, sorry, and apart from that 1, 0, 1, 2. So this is what queue contains initially. Now after this BFS ends, after this for example when we start from 0, 0 and discover and move one step, so we find this and this, two zeros we find, so none of them is 1. We move to the next and next we store the value of these were already in the queue, so we store their values. After that we move to the next element 0, 1, and there we see that there is 1, 1. So we pop this item. We pop this item from the queue. So queue transitions like this. Let me write it here. So queue becomes, after it has visited 0, 0, it becomes 0, 1, 0, 2, 1, 0, 1, 2. Because it did not encounter anyone. Now next stage 0, 1 will be checked. From 0, 1, we can see that 1 is near at a distance of 1 from 0, 1 index. So we will put this into the queue at the end. So we are popping from here, from the front. So queue will become like this. Queue equals, the three things will be copied as it is, and we will add the new number 1, 1 to the queue. Now next element will be checked 0, 2. So nothing is from 0, 2. No one is at a distance of 1 from 0, 2 index. So it will simply pop up and nothing will be added to the queue. Next it check from 1, 0. So from 1, 0 it sees that 1, 1 is there, and also this 2, 0 is also there. So now it will add one more element to the queue. So 1, 0 will vanish, will pop away. The two elements will be copied, plus one more will be added, and that is 0, 2, 0. Now next 1, 2 will be checked. So there is 2, 2. 2, 1 is there. So first of all, it will pop, and 2, 1 is there. So 2, 1 will be inserted into the queue. Now 1, 1. So row 1 column 2. Not from row 1 column 2. I think we did a mistake here. So it will check the nearest one from row 1 column 2. That is this number. From here we can see that here this is the nearest one. So Q will be adding 1, 2 will popped up, but it will add one more index, that is 2, 2. Now it will check 1, 1, and from there it will get 2, 1. But it will not be added in the front but at the last. So 2, 1 will be added, and 1, 1 will be popped up. So in this way, and now after that, it will check 2, 0. So there is nothing to add because it reaches the end of the matrix. So it will be popped up. 2, 0 will be popped up. Then 2, 2 will be popped up. And finally 2, 1 will also be popped up. Now Q becomes empty, so the loop ends. And we have got the distance matrix as this. Now this is our final answer. Now let us discuss time complexity. There are m rows and n columns. Every cell is added to the queue at most once. We are discussing the time complexity. Every cell is added to the queue at most once. For every cell, we check 4 directions. So the time complexity is O order of m star n. Because every cell is visited just once and only 4 directions are being checked. So that is a constant. So time complexity will be bounded by m into n. Now space complexity, we use a distance matrix to output the result. So it is also, and the size of that matrix is m star n. So space complexity is also the same. Now let us try to run the code. Okay, so it is wrong for the space too. Let us see how. Okay, so we are getting the output as minus 1, minus 1, minus 1, and it should be 1, comma 2, comma 1. How is this happening? Okay, so we have written this if statement outside the for loop. We have to keep it inside the for loop. Let's test it again. Okay, now let's submit the code, and it has been accepted. All the test cases have passed. Now finally let's discuss some common mistakes that are made while solving this problem. So first mistake is starting BFS from everyone. That brute force idea is very slow. That works, but it is not optimal. The better idea is to start BFS from all zeros together. Second mistake is forgetting that movement is only in 4 directions. We can move up, down, left, and right. We cannot move diagonally. Third mistake is not checking matrix boundaries properly. For every new row and new column, always check new row should be between 0 and rows, and new calls should be greater than equal to 0 and less than calls. Here rows and calls are exclusive upper limits. So new row equals to rows is invalid and new call equals to calls is invalid. Mistake number 4 is using the original matrix to track visit sales. So without thinking carefully. It is cleaner to use a separate distance matrix. Here minus 1 means unvisited. And finally one more mistake is made, updating the same cell again and again. So in BFS, the first time we reach a cell, we already have its shorter distance. So we should only update a cell when distance uh, at that value is minus 1. And one more mistake is there that sometimes using a normal list as a queue and doing pop 0. This can be slow because pop 0 shifts all elements, use deque from collections, and use pop left. Now let us conclude. In this problem, we learned that a matrix can be treated like a graph. Each cell is a node. Each cell is connected to its top, bottom, left, and right neighbors. Because we need the shortest distance, BFS is a natural choice. And because we have many zero cells, we use multi-source BFS. So the core idea is put all zero cells into the queue first, then let BFS spread level by level. The first time a cell is reached, then that is its nearest distance from zero. So this is LeetCode 54201 matrix, a very important problem for learning grid BFS. in multi-source BFS.